Good morning, I am Davide Dermit and my tutor is Professor Borgarino. Today I will explain you the design of two frequency dividers working in the Ku band. I will begin the presentation with a brief explanation of the PLL as a block diagram, and then I will pass to analyze the two dividers realized. These dividers were realized in cooperation with the University of Nice, France, and they are at the moment under test. I will conclude my presentation with the description of another type of the PLL, the digital PLL. I worked on this research field during a 7-month internship at RF Magic, Sophia Antipoli, France. Okay, the PLL can be represented simply as depicted in this slide. So we have the PFD block, which determines the phase and frequency differences between the reference signal and the feedback signal. Then the output of the PFD charge pump block is averaged from an analog loop filter, and this generates the tuning voltage for the voltage control oscillator. And then the output of the VCO is divided down in frequency by the frequency divider and fed back to the input. And so the divider is a fundamental building block of the PLL. And we can design both divider with fixed division module or with variable division module. Let's start from the first divider. It is a fixed modulus divided by 4 circuit. It receives an input signal at 15 gigahertz and the supply voltage is 1.2 volt. The load that has to be driven is 50 ohm parallel 90 femtofarad, which is an estimation of the pad capacitance. This is the architecture chosen. We can see 2 D latches connected in a master-slave configuration, and so this architecture is able to divide by 2 the frequency of the input signal. I have chosen this architecture since for each path you can see that only 2 devices are stacked from VDD to the ground, and so this is a useful feature since, as I said, the supply voltage is limited to 1.2 volt. Here just some simulation result. We can see this simulation is done in all typical case at room temperature. On the bottom of the figure you can see the input frequency of 15 gig, and then going bottom up you can see the output of the first division stage, so 15 divided by 2 gigahertz, and finally the output of the whole prescaler that is on the top of the figure and is the input frequency divided by 4. Here just the layout view and the corresponding chip microphotograph. The other prescaler, as I said, is divided by 2 3 dual modulus prescaler, and the supply voltage and the load are exactly the same, but it receives an input signal with a frequency of 12 gigahertz. The architecture chosen in this case is for the D flip-flop is just obtained from a set reset latch with the addition of 2 3 inputs ends, and then applying to the picture on the left the Morgan rules, we can obtain the CMOS cell shown on the right. And this is a D flip-flop, so cascading 2 of this stage in a master-slave configuration as before, we obtain a divide by 2 circuit, and then interposing some logic, we can, between 2 divide by 2 circuit, the dual modulus prescaler is obtained, and the division modulus is controlled by a binary external signal called modulus control. Again, we can see the input frequency on the bottom of the figure at 12 gig, and then in the middle of the figure the output when the circuit is set to divide by 2, and on the top when the circuit is set to divide by 3. Here we have again the layout view and the chip microphotograph. And now I will explain a very brief explanation of what DPLL is. I have researched in this field, as I said, at RF Magic in France. Unfortunately, I cannot show the result obtained since I have signed a non-disclosure agreement with them. But what I can see is that the technological process available today allows to scale very much the dimension and integrate and design very well digital circuit. So using mainly digital circuit in a SIP allows to shrink the size and to reduce the power consumption. Therefore, in the past years, a lot of research were carried out to try to substitute to an analog PLL as the one that I have showed you before, corresponding all digital PLL. Unfortunately, substituting some blocks such as the VCO with an all digital counterpart is not easy at all, and so PLL as the one depicted here can be used. Here the PFD is substituted by the TDC, which is a digital machine that determines the difference between the reference and the feedback signal in terms of its time resolution. The output of this block is then low-pass filtered by a digital filter this time, and this is a great advantage since in the analog PLL a lot of space is occupied by the analog loop filter, so substituting it with a digital counterpart allows to shrink a lot the dimension. But here the VCO is an analog circuit, so we have to convert the output of the loop filter, that is a digital number, with the tuning control voltage, and so there is a DAC between them. And as before, the output of the VCO is divided down in frequency and fed back to the input by the frequency divider. With the list of publication, my presentation concludes. I would like to thank the University of Nice and the guys at RF Magic, and obviously to thank you all for your attention. If you have any question, yeah, thank you. Maybe we don't decided yet because we have anyway some work to do. We have at now developed a system level simulation, and only few blocks were really designed on Cadence, so maybe the publication can arrive, but later surely. Yeah.